that we have solved a couple of questions regarding the equation of wave. Okay, now let's go over to the next thing. Wave speed and medium. So far we have been talking about, let's say, a transverse wave equation. Okay, let's say of this kind. So if you remember, we have studied that frequency of the wave is actually the same as frequency of the source. That is, in other words, you can say that frequency of wave depends on source and nothing else. Right? Frequency of wave depends on source and nothing else. Right? Okay, that is, the wave takes the same frequency as the source oscillates. Fine. But what about wave speed? Right? And then further wavelength. Right? What about wave speed and wavelength? You see, wave speed is something that depends on medium. I repeat, wave speed, let me just put it here clearly. Wave speed or propagation speed depends on properties of medium. Okay, that's the key thing. Not on source. Right? Wave speed depends on the properties of medium and does not depend on in any way on the source. Right? What this means is that if you consider that there is a source, let's say here, and there is some medium, right? And there is some wave traveling in the medium, let's say sound wave or any other wave. So far we have learned that if this is the equation of the simple harmonic wave, then we find that the frequency of the wave is always the same as frequency of source. Frequency of the wave is always the same as frequency of the source. Right? That would mean that whatever is the frequency of wave, that depends only on the source and nothing else. Right? Whether that wave is created on a string or in water or in air, all that, the medium is not important. Again, the medium or anything else, or even observer. Observer means the one who gets that wave or the one who sees that wave. All these things, they don't affect frequency of the wave. Okay? Because that depends on source. But when it comes to wave speed, the wave speed depends on the properties of the medium and not on the source. That is, it's like the source only plays the role of generating the waves. Okay, and then with what speed they move, that depends on medium, not on source. I repeat what I've said. Source plays the role of generating the waves, that's it. Okay, it will generate it, its task is over. Then the medium makes the wave propagate, because you see, ultimately when a wave travels on a medium, it is that the particles of the medium will apply forces on each other, and that's how the disturbance moves forward. I repeat, for example, let's say the source is like this at some point of time, and these are some particles of the medium. Then between source and particle number 1 there will be some attraction, there will be some force. Because of that force, this particle number 1 will rise. Does that make sense? Yes or no? Because of that, the particle number 1 will rise. Clear? So, how the wave travels depends on the properties of the medium and not on the source. Two things completely clear. F depends on source and V, wave speed, depends on medium. Clear or not clear? Okay, what about the third thing? Wavelength. What about wavelength then? What about wavelength? So you see, wavelength is kind of nowhere. That is, it is something that is explicitly decided by two other quantities. I repeat, wavelength of a wave is not independent. Okay, it is decided. It depends completely on two other quantities. Which two? Wavelength depends on frequency and wave speed. I repeat, wavelength is something that completely depends on these two quantities, frequency and wave speed. Alright? Okay, so if someone would ask you what does wavelength depend on, then you can say source decides frequency, medium decides wave speed, and together these two properties decide wavelength. So indirectly you can say wavelength depends on both. Did you understand? Wavelength depends on both the source and also on the medium. Clear or not clear? No, Aditya, that is not true. The question was that if we apply more force, on the source, let's say you pull it harder, okay, in one case you are making this oscillate on the string in some way, and in second case you are making it oscillate like this. So in both these cases you might be applying more force at some times on the source, no problem. But source has absolutely no control over wave speed. Let me make it very clear. Whatever happens to the source has nothing to do with wave speed. Understood? Okay? Right? Because wave travels by the interactions of molecules with each other. I'll repeat that part again. A wave can travel in a medium only because of passing the energy, or basically intermolecular forces between the molecules of the medium, right? So what you do to the source has no effect over here. Is that clear? So that's why more force on the source does not change the wave speed, right? In fact, doing anything to the source cannot change wave speed. Let me make it clear. Doing anything to the source cannot change wave speed. Wave speed is decided completely by the medium. Got it? Okay, so now if wave speed depends on medium, like I have been saying, then which are the properties that we need to talk about? Okay, let's see. Suppose there is a string and there is a transverse wave on string. There is a transverse wave on a string. Okay, then it has been found experimentally. We are not going into it. It's not that tough to check even at home, right? And definitely describe the method, right? Or even better, I might show it to you in animation the next time. All right? I think that will be better. Transverse wave on string. Okay. So let's say there is a transverse wave on string. It has been found that wave speed depends on following two quantities only. Wave speed depends on following two quantities only. One, tension in string. Right? It depends on tension in string and on the linear mass density. Linear mass density, that is mass per unit length. Okay, so it only depends on these two things, right? Tension in the string and on linear mass density. Okay, right? And now we see the actual proof of what we are going to do. I mean, the relation that we will get, the actual proof is not in your syllabus. Okay, because it needs a complicated bit of mathematical equations which you need to solve. So here we will just do a dimensional analysis approach. Remember, it is not the proof. Someone might say this is the proof. No, I say this is not called a proof. A dimensional analysis proof is not a proof. Remember that. Okay, so this is just some basic idea. This is just some basic idea, okay, of what we should expect. Let's see. So V somehow depends on what tension T in the spring. Let's say T raised to A, okay, and on linear mass density. Now, probably in 11th standard, like we studied the chapter center of mass, or in gravitation, at some case we have come across linear mass density, right? It is mass per unit length. We might be writing lambda over there, I know. But now I will not use lambda because lambda stands for wavelength. There is a chance of confusion. So let me write mu. I repeat, I am writing mu for linear mass density. Okay, linear mass density is mu. I am not writing lambda like I might have written earlier because lambda now is wavelength in this chapter. Okay, so now we are going to solve this dimensionally. So velocities dimensions are m raised to 0, L raised to 1, T raised to minus 1. I am sure you all know this. Tension is a force. Okay, so tension is a force. Its dimensions are going to be T, that is force, that is m raised to 1, L raised to 1, T raised to minus 2. Okay, force raised to A. And linear mass density means mass per unit length. So m raised to 1 per length, that is L raised to minus 1, the whole raised to B. So dimensionally this is what we should have, right? Proportionality is removed, we get a dimensional constant. I am not going into all that, you have studied that in second chapter. Okay, anyway. So this becomes m raised to A plus B, have a look. L raised to A minus B, okay, and T raised to minus 2A. I hope that is clear. I have combined powers of m, 1A, 1B, so A plus B, 1A and 1 minus 1B, so A minus B, and here minus 2A, T raised to minus 2A. So if we just compare the powers on both the sides, if we compare the powers on both sides, okay, we are getting A plus B is 0, we are getting A minus B is 1, and we are getting minus 2A is minus 1, isn't it? Okay, third one is easiest to solve, let's attack from here. Therefore, A is going to be 1 by 2. Understood? A is going to be 1 by 2 if we go and put it here. If we go and put it here, right? What do we get? 1 by 2 minus B is equal to 1. That will give me B is equal to minus 1 by 2. Clear? Okay, everyone. We have got two powers, one for T, one for mu. Okay? So, finally, if we combine all of this, we get a relation as follows. This would be V will be equal to T raised to half, means root of T, and D raised to minus 1 by 2, D is minus 1 by 2, so mu raised to minus 1 by 2. So T raised to 1 by 2, mu raised to minus 1 by 2, which you can also write as root of T upon mu. Alright? So this is in fact the experimentally verified formula. Okay? Alright everyone. So this is the one thing that I want you to remember. Again, this is not the proof, like I mentioned. If someone says this is a proof, no problem. Yeah, you can have good luck. It's not called a proof. This is just dimensional analysis, right? It could easily have been 3 root T by mu, but dimensional analysis of course does not tell you whether there is a 3 or not. Also, experimentally this turns out to be true. Okay, experimentally also it turns out to be true that there is no constant anywhere. That is, it's not like this, it's not like this also. Alright? So this is the formula for this transverse wave on a string. Is that clear? What is this formula for? Transverse wave on a string. Okay, what are the terms? What are the terms? Let's write the terms. V for wave speed. Okay, of transverse wave. Please write that. Of transverse wave on a string. Let's make it absolutely clear. Then T for tension in the string. T for tension in the string. And last one, mu for linear mass density. Okay, or mass per unit length. So these are the things. Alright, everyone noted it down. Okay, that's it. Now, let's go to the second part of this topic. Okay. Speed of longitudinal waves in fluid. Okay, speed of longitudinal waves in fluid. This topic is definitely of some importance. Which derivation are you talking about? Which derivation are you talking about? That's not a derivation, it's just a verification of velocities dimensions. Okay? So, yeah, it could be there. There's nothing extraordinary about it, it's just dimensional analysis like you have in the second chapter. Okay, anyways, so let's come to this point, speed of longitudinal waves in fluid. Okay, why is this important? Fluid means what? Do you remember? Which kinds of states of matter are included in fluid? Which kinds of states of matter are included in fluid? Which kinds of states of matter are included in fluid? Yes, very good. So either liquid or gas. Okay, either liquid or gas. So this topic is of huge importance because of the fact that sound in air or in any other gas, or even frankly in a liquid, right? In any gas or in any liquid, sound is longitudinal. In any gas or in liquid, sound is a longitudinal wave. In solids, well, it's not that simple. Okay, right? In solid, sound wave may be transverse. All right. Anyways, coming to this here, so this is important for us because we're going to deal with sound. You know, sound is one of the most common waves that we notice in our life, right? So sound is a longitudinal wave when it comes for traveling in gases or liquids. Now let's see what's the thing here. For speed of longitudinal waves like sound in fluid, it has been found, listen to this carefully, for speed of longitudinal waves in fluids, it has been found that the speed depends on, the wave speed depends on two things. Number one, modulus of elasticity. Modulus of elasticity, right? And the second thing that it depends on is density of medium or material, right? So it has been found again experimentally, purely experimental, this relation, okay? And like I said it earlier, we are not going to derive it actually, which is just a dimensional analysis approach. So we depend on modulus of elasticity and density of material. So if we do something like we did it earlier, so V proportional. Now modulus of elasticity in a gas or a liquid cannot be Young's modulus, cannot be shear modulus. Hopefully you remember these things, right? We only need to use the third one for modulus of elasticity in a gas or a liquid. Clear or not clear? Do you remember in properties of solids or properties of matter, we have studied this, that Young modulus and shear modulus are only valid for solids, isn't it? Clear? Okay, so we will use the bulk modulus. As modulus of elasticity for gas or liquid, it's going to be the bulk modulus. So B raised to A and density, that is rho for density, raised to B. Okay. Now, if you remember formula of bulk modulus, I'm sure you do that. It's minus delta P by delta V into V, isn't it? Minus delta P by delta V multiplied by V. Okay. So here dimensionally, I hope you realize that volume and volume will get cancelled and only dimensions of pressure, right? In other terms, if you remember, unit of bulk modulus was Pascal. Do you remember that? Pascal, that is pressure. So dimensions of bulk modulus are same as pressure. M raised to 1, L raised to minus 1, T raised to minus 2, same as pressure, raised to A. Density, mass per volume, so M raised to 1, M raised to minus 3, the whole raised to B. So this is going to give me L raised to 1, T raised to minus 1. So once again, similar procedure, right? Okay, so here you have M raised to 0, L raised to 1, T raised to minus 1 equal to M raised to A plus B, L raised to minus A minus 3B, and T raised to minus 2B. Right? And by similar ideas, once again, we will have minus 2A equal to minus 1. I am comparing T with T first of all. So A is equal to 1 by 2. Okay, A is equal to 1 by 2. Now compare M with M. So 0 is equal to A plus B, therefore 0 equal to half plus B, therefore B is minus 1 by 2. So A is 1 by 2, B is minus 1 by 2. If you do the same thing here, do you realize that you are going to get like this? Clear? Clear or not clear? Okay. Now let's write down the terms. V for wave speed of longitudinal wave in fluid. Actually this is not just true for fluid. This relation, listen to this carefully, this relation is also true for solids, right? But it should be a longitudinal wave. I repeat, this relation is also true for solids, but it should be a longitudinal wave. So in general, it's true for all longitudinal waves, right? It is true for all longitudinal waves. But in solids, the longitudinal waves are fairly rare. Okay, it's not like they're impossible, not like I cannot give you an example, I can. Do you remember that example of slinky? Do you remember this or not? If you push this over here, compress it, then a wave pulse will travel. Do you remember that or not? Okay? So it's not like longitudinal waves are not there in solids, they are there. But the natural examples are not so many. One natural example that I can think of is, earthquake, right? Okay, one type of earthquake wave is longitudinal, and obviously it travels in solid. The crust of Earth is solid. Anyways, so this is in general the speed of longitudinal wave, right? Rho for density of the medium or material, of course, right? And finally, B is bulk modulus, okay, of that material. B is bulk modulus of that material. Clear? All terms? Now you see, you have to be careful remembering these formulas. Confusions may occur if you misunderstand the question a little bit, or in a hurry you use a different formula. That's also possible, because now there are two already, right? Okay, there are two already, right? So if you recall, we have talked about two cases, one of a transverse wave on string and the other is longitudinal waves in materials. Okay, all kinds of materials, this is same formula, right? Now we are going to very specifically talk about it. We are going to very specifically talk about speed of sound. Okay, so all this is still the same topic, wave speed and its relation with the medium. You can see these are properties of medium. Do you see that, everyone? B and rho, they are properties of medium. Do they depend on source? Think about it. Does bulk modulus of material depend on source? Does density of material depend on source? Alright, so hopefully what we wrote earlier is clear, that source does not affect wave speed in any way. Right? Wave speed depends only on the properties of material. Right? Whether you see this formula or the previous one. Right? Okay. Now, the third part of this topic, specifically about sound. Okay? Speed of sound in gas. Okay, any kind of gas. Air, oxygen gas, nitrogen gas, blah blah blah, whatever. Okay. So further here we have Newton's formula first of all. Okay, Newton's formula. So obviously sound travels, you cannot see air, right? I mean, you cannot see the air molecules, but based on his observation, Newton thought that when sound passes, air undergoes, according to Newton, when sound passes, air undergoes isothermal expansion and compression. So this was his idea. This was Newton's idea. I repeat, in thermodynamics chapter we have already studied what is isothermal. Okay, so I am not going to explain all that, right? So Newton considered that when sound is created and sound travels through air or gas. Do you remember I told you at start that when there is an when there is a longitudinal wave, the medium compresses and expands. Do you remember that? Medium compresses and expands alternatively. Do you remember that idea? Compression and rarefaction. Okay, hopefully you do. I mentioned it at the start, even while I was explaining what happens to the sling. Right? Okay. So, building up on that idea, it is that he considered these two, expansion of air, compression of air, as isothermal. Now, if it is isothermal, we know temperature should remain constant. Is that clear or not clear? Temperature should remain constant. Okay, and then assuming ideal behavior, we can derive the formula of B and put it over there. Right? That's what we are going to do. So we are now talking about a very specific case of this formula. We are now talking about so I was saying that this is in general for all longitudinal waves. Now we are going to derive a specific formula using this for sound, okay, and in gas typically, right? So T is constant if you consider the isothermal expansion or compression. Let's try again. So we have this as isothermal process, so temperature is constant, right? Now, if temperature is constant, we are going to try and find out value of B. Have a look here. B, its definition is minus V dP by dV. Alright? Instead of writing delta P by delta V, I can also write dP by dV. I hope nobody has any problem with this. Okay? And then for an ideal gas, I am going to use the formula of pressure over here. So I wrote it in here that the bulk modulus is equal to minus V dP by dV. Now we are going to use the ideal gas equation, okay, assuming that air or any other gas is ideal, right? And then we will simplify this, right? So first of all, for ideal gas equation, we have P is equal to PV equal to nRT, right, or mu RT, as you may be writing. Again, I am not writing mu here because we have used mu for linear mass density, so it's always going to be some confusion. So anyways, so if I want to find what is dP by dV, right? Okay, if I want to find what is dP by dV, then I can write this E as nRT upon V. Okay, but that can further be written as nRT V raised to minus 1. Clear or not clear? Right? Okay, because V is divided, so you can write it as V raised to minus 1. So now if I do differentiation of T with respect to V, constants simply kicked out. So number of moles always a constant, gas constant, temperature is constant, isothermal process, and V raised to minus 1's differentiation is V raised to minus 2 and then that is into minus 1. Clear? This step is clear, everyone? Differentiation of V raised to minus 1 is minus 1, V raised to minus 2. Okay? Well, let's simplify this further. Therefore, dP by dV is equal to minus. What is nRT? What is nRT? PV, isn't it? Okay, so PV V raised to minus 2. Again, nRT is PV by ideal gas equation. So we get this, which is ultimately minus P upon V. Clear or not clear, everyone? Minus P V raised to minus 1. So minus P upon V. Got it? Yes, no, people. I am waiting for your response. Okay, let's put it in bulk modulus. So I get therefore B equals from here minus V into dP by dt is minus T by V. Okay, so V cancel and minus plus, so we got amazingly simple relation here, right? It is that for isothermal process on a gas, ideal gas. Okay, remember this is only true for isothermal process on ideal gas. We have got a very simple relation that bulk modulus is same as pressure, right? So if we use it in that formula of wave speed, therefore according to Newton, speed of sound in gas should be V equal to under root V by rho. Okay, but what is B equal to? B is equal to P. So V equal to under root P by rho. P for pressure, rho for density. Right? P for pressure and rho for density. Okay, clear so far, everyone? Clear so far or not? Okay, it's not the final formula though, okay? We'll have to wait a little bit before we get to the final thing. Okay, I'm going to erase this now. From here, hopefully you have noted all this, right? Okay, now further I'm going to simplify what is P by rho. Okay, I'm going to simplify what is P by rho for ideal gas. Okay, P by rho for ideal gas. Okay, have a look. Rho can be written as mass upon volume, isn't it? And P, you know, P is equal to nRT by V. Clear for ideal gas? Alright? So this will give me V, small v, wave speed equal to, if I put P's value and if I put rho's value, okay? nRT by V is pressure, M upon V is density. V cancelled. Okay, further, this is capital M stands for mass. Remember, here we have written mass upon volume. So capital M is the mass of the whole gas, whatever that is. Then I can write N, small n, number of moles, as mass upon molar mass. Do you remember this equation from kinetic theory of gases or from thermodynamics? Small n equal to m upon m0. Okay or not okay? So if we use it here, V equals V cancelled under root m RT by m0 m. Okay, nRT by m0 m. V is cancelled. Instead of n, I am writing this. So mm also cancelled, and we get V equal to under root RT by m0. Right? Okay, so finally, this whole thing is called Newton's formula. Okay, this whole thing is called Newton's formula. What? V equal to under root P by rho and equal to under root RT by m0. You can use whichever form you like. Okay, what is this? V is the speed of sound in gas. Okay, alright. P for pressure of the gas, rho for density of the gas again, R, you know very well what is R. T for absolute temperature, everyone. Do not put it in degree Celsius. Do not put it in degree Celsius, in Kelvin only. And M0 for molar mass of gas. Molar mass of gas. If you fancy thermodynamics, you can write it in one more way. Okay, I am not going to explain how we get it. If you remember thermodynamics things, you will probably understand how we got there. R, Kb, M0, small m, hopefully you remember. Okay, we used to have similar equations for VRMS, correct or not? we used to have similar equations for VRMS for gas. Okay, so this is Newton's formula, right? This is Newton's formula about speed of sound in gas, right? About speed of sound in gas. Now, you see, this is not perfect, right? There is about 10% or so error. Let me tell you that. Okay, all this makes nice theory, but when this formula is experimentally verified, that is, you check whether actually sound speed is just this, right? That you put value of R, you put some temperature, you put molar mass. Okay, is it really matching? No, there is some 10% or so error, right? So Newton's formula is not totally wrong, not rubbish, but there is some error, right? So then next time, we will discuss something called Laplace correction or Laplace's correction. Okay, what that means is that Laplace, name of a person of course, he thought that okay, well, this is not the proper idea, right? So he modified Newton's idea a little bit and derived his own formula of speed of sound. Okay, his own formula of speed of sound, and that works perfect, right? So like I said, this is slightly wrong, about 10% error over here. Okay, but Laplace formula, which is also called Laplace's correction because he corrected Newton, right? That formula works better. We will derive it the next time. Alright, goodbye everyone.